Hello everyone, welcome to week 11 spread spectrum communication problem solving session. Today we will be doing multi-user detection and IS95 and CDMA2000 standards. So these are the three topics: multi-user detection, IS95 and CDMA2000. So we will be going straight to multi-user detection. Okay. So here we have CDMA in summary. CDMA or port division multiple access. So CDMA entails multiple users, each having their users, each having their assigned code, transmit their data together in a common channel. Remultiplying their data with so in effect the channel looks like this. User 1 it transmits C1 into D1, so C1 is its code. Similarly, there is a user 2, it transmits C2 into D2 because its code is C2. user 3 C3D3 and user 4 C4D4. So the total data will be C1D1 plus C2D2 plus C3D3 plus C4D4. So this is your total data, capital D. So this is transmitted onto the channel, and at the receiver, you have, say, if there is R1, which is the intended receiver for user 1, then it will multiply C1D1 and it will multiply C1 and such that C1 plus C1 will be 1. So C1 dot C1D1 plus but C1 dot C2 will be 0. Similarly, C1 dot C3 will be 0. So the C1, C2, C3, C4 should be orthonormal. Orthonormal. So this will give D1. So you can see receiver 1 will receive D1. But as C1 into C2 is 0, C1 into C3 is 0, C1 into C4 is 0. So this is the basic essence of CDMA system. Next, now this multi-user framework for CDMA system. So with this multi-user system that we have, the detection of that is can be systematically done with matched filters. So here we will be studying the matched filter detection of multi-user CDMA systems. Okay, so the next part is a basic CDMA user channel will consist of k users, which is given as follows. So SKT is the signal that is assigned to the kth user, and AK is the received amplitude or RSSI, and BK is the bit transmitted. So each user K wants to transmit a bit BK that will be modulated by a waveform SK, and finally that will have some gains and losses which will together be incorporated in the amplitude AK. So the received CDMA signal will be a summation of all these YT signals, and along with that there will be a noise. So multi-user detectors usually have a front end whose objective is to obtain a discrete time process from the received continuous time waveform. So there is a continuous time waveform here. You have to create a discrete time processes corresponding to each user from this. So the synchronous model is that you design match filter for each of the user at the each of the transmitter users, and then you pass the entire waveform through this bank of match filters, and it is expected ideally that each match filter will separate out the data that is meant for its user and reject the data that is not meant for that user. So So each of the match filter will give an output which is the integration of SKT, which is the waveform for that user. So you have designed a match filter means you have matched with the transmitted waveform. So once you do that, you will get y1, which is the correlated output of the received and the original waveform of the user one. So each user has its original waveform that will be correlated with the receiver. Okay, so the receiver will okay. So each of them will give us outputs y1, y2, y3, like that, yk. And using this equation we can express the output of the kth match filter as akbk plus some error term. So akbk is the amplitude and the bit of the kth user, which is exactly what we want. We want the scaled bipolar bit. So like if you receive minus 2.5, you can say that it is actually minus 1, which is bit 0. So if you receive minus 2.5, you can say bit 0 was transmitted. If you receive plus 3.5, you can say bit 1 was transmitted. So this scaled bit value is what we want from an ideal match filter. But of course, there will be some noise term and there will be some error term. So if they are not perfectly orthogonal, then there is no cross correlation between the waveforms, then you will of course get the exact bit plus noise. But if you have some cross correlation between the waveforms of the different users, which you practically will have, then you will have an error term which is denoted as summation j not equal to k. So j is all other users except for user k. So summation j not equal to k aj bj, so the data for the other user, into rho jk, which is the cross correlation between the j and the k user, plus nk, which is the Gaussian noise. So if you can exclude this error term, then you will see that this match filter is giving the exact output that is needed except for the error term. So the design of the match filter lies in the fact how small you can design of the waveforms rather. Design of the waveforms lies in the fact that how well you can minimize the cross correlation between two waveforms. The smaller the cross correlation is between two waveforms, the better the error detection will be. So the conventional single user match filter receiver requires no knowledge beyond the signature waveform and timing of user wants to demodulate. The multi-user CDMA receiver model consists of a bank of mesh filter with outputs which are modeled as random variables. It is widely believed that so you will get outputs which are believed to be random variables because you don't know the data. The data is random. It is widely believed that the decision of conventional single-use mesh filter were, if not optimal, almost optimal for a channel with a large number of equal power users. So if you have a large number of equal power users, then your mesh filter is, if not optimal, there is it is nearly optimal. Okay. So, but later it was proven that this conclusion of near optimality of the single user mesh filter originates from the implicit assumption made that observable used to demodulate user 1 must be that the observable used to demodulate user 1 must be restricted to its mesh filter output. So that means basically whatever you have used here, it is the assumption is that it has to be perfectly reproduced because you don't have the exact waveform at the transmitter, you have to receive it locally. So if you can perfectly reproduce the signature waveform of the user at the transmitter sitting at the receiver, then if you can perfectly reproduce the transmitter signature waveform, then you will of course have very good performance for matched filter, near optimal performance for matched filter. So YK is not a sufficient statistics for BK. So YK alone cannot give you the exact inference about the value of BK. So next there is another type of channel, detector, which is the two user synchronous channel detector. So here you will take two users instead of multiple users, and we will go through that. বল भाई मेरा मीटिंग चल रहा है इससे मैं नहीं मैं नहीं यार sorry for the interruption. I had some brief task to handle. So I will start the class again. So the two, as I said, the two user synchronous channel is yt equal to a1 b1 is 1 2 plus a2 b2 is 2 t. The minimum probability of error decision user 1 is with the possible different optima. However, this optima which we shall. Okay, so you see that the first we had only one single user and for one filter, and we had made a bank of filter with each filter corresponding to a single user. So if you have k users, you will have k filter in the filter bank, and then that was assumed to be mere ideal if we can generate the waveform accordingly. But then there comes the second type of detection, which is two user synchronous channel. So if there are two users, which is a1 b1 plus a2 b2, the minimum probability of error, previously it was multi-user, now you are saying it is two user. So two user synchronous channel will have a1 b1 s1 t, where s1 is the waveform, b1 is the bit, and a1 is the amplitude. The maximum minimum probability of error decision for user 1 is obtained by selecting the value b1 equal to -1 plus 1 that maximizes the a posteriori probability. We could pose a different optimum detection problem by requiring that the receiver selects the pair that maximizes the joint a posteriori probability. Let us okay, so we will have the minimum probability of error for user 1 is obtained by selecting the value of b1 that maximizes the a posteriori probability. So user 1 here will have to make a decision, and it will make an erroneous decision if it detects -1 instead of +1 or +1 instead of -1. So that is determined by maximizing this a posteriori probability given in 1.4. And we can jointly for user 2 also this will be there, so we can jointly say that we have to the receiver will select the pair that maximizes the joint a posteriori probability b1 b2 given yt. However, these optimum detection strategies, which we shall refer to as individually optimum and jointly optimum, need the result in same decisions. Okay, so first there is a joint optimum decision. In joint optimum decision, you will have four possible values of b1 b2: +1 -1, -1 -1, -1 +1, and +1 +1. Okay, the Okay, so if you want to solve the jointly optimum problem, solve decision problems, then there are four possible values: a1 s1 plus a2 s2, a1 s1 minus a2 s2, and so on. So the likelihood function for selecting the pair is given by this. So yt minus, so you have this Gaussian likelihood, and the joint optimum decision is such that the received signal is closest to a1 b1 st plus a2 b2 st. Okay, the minimum distance decision. So the regions are shown. So you have to choose the one which will, of course, minimize this distance. Okay. So let us see how to implement optimum decision rule that selects the closest hypothetical hypothesis to the observation. The likelihood functions can be expressed as this. So this is the likelihood function with the matched filter outputs denoted by yk equal to ytst, and rho represents cross correlation. Okay, to maximize the right hand side of equation 1.7, we can disregard the factors that do not depend on b1 b2. So we can disregard this uh, second term, and we can disregard the we thus the maximum likelihood decisions are those that maximize the function omega 2. So we can disregard the second and third term. So we only, because third term is a received signal, direct received signal whatever you are getting, and the second term only depends on a1 and a2. So it is basically the omega 2, this omega 2 function b1 a1 y1 plus b2 a2 y2 minus b1 b2 a1 a2 rho. Whatever maximizes this function will maximize the likelihood, a posteriori likelihood, and the solution for that is b1 hat equal to signum y1 and b2 hat equal to signum y2. So what is the signum y1 symbol? What is the y1 symbol? That will be your b1, and what will be the y2 symbol will be your b2. So what is y1 and y2? Y1 and y2 are the individually optimum decisions that we have done from the single user. So matched filter output basically. So the matched filter output or single user output, that is y1 and y2. So if we take the matched filter output, multiply with them with b1 a1 and b2 a2, and subtract this b1 b2 a1 a2 rho term, then we will get omega 2. Now the maximum of that can be expressed by differentiating this with b1 and with b2. So if you differentiate it with b1 and b2, you will get a1 a2 rho. So says that if more okay, so if you solve that, you will get b1 equal to signum y1 and b2 equal to signum y2. Okay, so whatever the match filter output is, the signum of that is your bipolar bit. So that is the decision rule. Okay, so now we will be covering more on the multi-user detector after we have finished IS95 and CDMA 2000. So for now we will stop our discussion on multi-user detector and now go to IS95 and CDMA 2000. So in the 1991, the US based company Qualcomm launched IS95, which is interim standard 95. And the the system became the first commercial implementation of CDMA. So now CDMA is a theoretical system that has been developed in academia, but the actual standard which has to come from the industry is the IS95 standard of CDMA. So the specific implementation of CDMA is the broad theoretical concept, and the specific standard of CDMA that was implemented is IS95. So I the hmm. So IS95 was adopted by a considerable number of operators, and by 2005 was used by two or the four major operators in the US. It is also obtained a dominant market position in South Korea. But the original IS95 system did not fully exploit the flexibility in CDMA system. However, later refinements and modification did make the system more flexible. So in the late 1990s, the need for further enhancement of data communication capabilities as the demand grew became more important. Okay, so CDMA seemed well suited for this approach. So the new third generation system was proposed, and CDMA was proposed as the implementation for third generation. Okay, so the people who came up with IS95 then developed CDMA into the CDMA 2000 standard, which was basically, you can say, the sequel to IS95. And there was also another standards, uh, which was called the wideband code division multiple access standard, WCDMA. So those who did not agree to IS95, they those who did not agree to IS95, they came up with WCDMA. And IS95 and WCTMA were the implementations, you can say, the implementations of proprietary implementations of the same open source technology. So they were proprietary, that means they could not be implemented one by another. They could not be not implemented, rather they could not be deployed in each other's systems, so they were fundamentally incompatible. So hardware made for IS95 standard was incompatible with WCDMA and so on and so forth. So thus there were two competing standards for CDMA. One was the CDMA 2000 and another is the WCDMA. So now we will come to IS95, which is the first CDMA implementation, which came before WCDMA and CDMA 2000. So IS95 is a CDMA system with an additional FDMA component. So the available frequency range is divided into bands of 1.25 kilohertz and megahertz, and duplexing is done in the frequency domain. So it is the first there is some frequency division going on, and within each band, traffic traffic control channels, and pilot channels are separated by different codes with which they are spread. So basically, you are transmitting data in FDMA, but the pilot channel, control channel, and all that, they are separated in code domain rather than frequency domain. So you are separating multiple data user data in frequency domain, but you are separating the pilot channel and control channel and all that in the domain, the mm, in the top code domain. So now IS95 considers two possible speech coder rates, 13.3 or 8.6 kbps. In both cases, okay, okay. Huh. Theoretically, each cell can sustain. So, because it is considering a maximum of 13.3 kbps speech rate, so it is that speech is spread by a factor of 64. Thus, you end up with 1.2288 megachips per second. So each cell, because each cell has a 1 point, yeah, so each cell will sustain 64 speech users. Okay, but in practice this number was reduced to 12 to 18 due to imperfect power control, non-orthogonality of spreading groups. So if everything was perfect, then in an ideal world it could have sustained this IS95 system could have sustained this 64 speech users. But because of the various non-idealities that are present, it can only sustain 18-19 users. Okay, so the downlink signals generated by one base station for different users are spread by different Howard Hadamard sequences. In the uplink, different users are separated by spreading codes that are not strictly orthogonal. Furthermore, interference. So, in the downlink, of course, the spreading is much more strict. The separation is much more strict. But in the uplink, of course, because the communication, like the detection capabilities of the transmitter of the base station is much better than the mobile users. So the uplink is not very strictly enforced separation in frequency or port domain, because even if there is imperfect separation, the transmitter, due to its superior detective capability, can decode the users. So yeah, what happened? No, no, tell me, tell me. You are also joining. Okay, so the traffic channel in IS95, the traffic channels and control channels are separated by different spreading codes. All base stations are synchronized using signals from GPS to obtain an accurate system time. So in the IS95, there is an additional FDMA component to where it uses frequency domain duplexing for separation of uplink. And so IS95 CDMA system has an additional FDMA component which uses frequency domain duplexing for separation of uplink and downlink. In the USA, IS95 operates in the 1850 to 1990 megahertz frequency band. This band is called the Personal Communication System band. The PCS band is divided into units of 50 kilohertz width, so that the center frequencies are related to channel numbers such as FC is equal to 1850 plus NCH into 0.05 and FC equal to 1930 plus NCH into 0.05 for the downlink. So uplink and downlink, the channel number can be correlated with the center frequency with this formula. So an IS95 system requires 1.25 megahertz, that is 25 of these channels. The preferred system frequencies are K equal to 25 with NCH with K equal to 1 to 47. So best is reserving 1 to 47, that is the preferred, but if you don't get that, then you will go for higher channel numbers. So IS95 also uses error correction coding as well as different types of spreading codes in order to express the source data rate, which is 8.6 or 13.3 to a chip rate of 1.2288 megachips per second. Encoding is usually done with a standard convolutional encoder, while spreading is done with MRE orthogonal queuing and multiplication by spreading sequence. So basically direct sequence spread spectrum, DS3, that we have read about. And another part of the IS CDMA system is power control. Power control is basically you separate the signals in power domain so that there is less crosstalk among the channels. So for this reason, IS95 foresees a quite involved power control procedure that is intended to make sure that large scale fitting and small scale fitting is compensated by power control. Okay. So there are two measures of this the quality of this power control. They are accuracy and speed. Accuracy indicates how much of the received power deviates from the ideal level in a steady state. Okay, so accuracy indicates how much of the received power deviates from the ideal steady state. So you want a particular amount of power to be present at the particular amount of time, so that that is the accuracy is that how accurately you can deliver that amount of power in that time. So next is speed. The speed of the power control determines how quickly power control can adapt to changing channel conditions. So okay. So, and the next is speed. Speed is how quickly your power control can adapt to the changing channel condition. So, if your channel condition changes suddenly, how quickly your power control can change your power. That is measured by the speed. So, accuracy and speed both need to be taken care of. So, there is an open loop mechanism of power control. So as we know, control is of two types. One is open loop and one is closed loop. So closed loop works on a feedback. Open loop does not need any feedback. So in open loop mechanism, the MS observes the power it receives from downlink signals, reaches a conclusion about the current path loss, and adjusts its transmit power accordingly. So it observes the power and adjusts its transmit to the power. So from the downlink signal, it will observe the path loss and the power, and it will adjust its transmit power accordingly. The only available method for controlling ms power at the start of a call in open loop power control. Okay, so in both loops, the BS observes the signal it receives from an MS and then sends a command that the mobile station adjusts the power appropriately. So the closed loop mechanism, the BS observes the signal and sends a command for it to adjust the power, whereas in the open loop system, it just observes the power and makes a decision on its own. So this is the closed loop. So in the closed loop power control, there is a inner loop and there is an outer loop. The base station observes the SINR and as a consequence requests an adjustment of the transmit power of the MS. The way, okay, so the inner loop is basically observing the SINR and requesting an adjustment of the transmit power from the MS of the mobile station, that is the user. Okay, and in the outer loop, the base so basically in the inner loop, it requests the mobile station to change its transmit power, and in the outer loop, it observes whether the transmit power has been changed by the mobile station or not. Okay, so now we come to pilot symbol. So pilot symbols are basically symbols, pre-agreed symbols that are transmitted before data transmission. These are basically trial messages. So these are like trial symbols that are transmitted, mostly to make conclusions about the mostly to make conclusion about the data set. Okay, so pilot signal, each base station sends out a pilot signal that the mobile station can use for timing acquisition, channel estimation, and to help with the handover process. The pilot signal has always been same form. The okay pilots from different base stations are offset with respect to each other. Okay, so coding before a speech signal can be transmitted over the air interface. It first has to be digitized and encoded. IS95 foresees the use of different speech coders. They have different bit rates. As spreading and modulation should not be affected by these different rates, it also implies that error correction coding has to be different. Okay, so before a speech signal is sent, so first the pilot is sent, of course. The pilot signal always has the same form that has been pre-agreed. From that, usually it is usually long enough so that pilots from other base stations are not confused with the long delayed echoes of the desired pilot. So yeah, so in now coding before a speech signal can be transmitted over the air interface, it first has to be digitized. Okay, so as spreading and modulation should not be affected by this different rate, it is also implies. So basically, speech is done at different rate, but you cannot do processing at different rate. All of them have to be uniformized. So to do that, before speech signal can be transmitted over the air, it has to be digitized and encoded. So that is the when you have to do coding. So uh, if you have multiple speech coders, each having different this. So as spreading and modulation should not be affected by these different rates, it also implies that error correction and coding has to be different. It has to be designed in such a way that the output from channel coder is always 19.2 kbps for downlink and 28.8 kbps for uplink. So whatever the rate of speech is that is coming, Irrespective of that, your coding encoding has to be in the vicinity of a 19.2 or 28.8 kbps. 19.2 for downlink and 28.8 for uplink. So IS95 uses a number of different speech encoder. The original system foresaw a voice coder with 8.6 kbps, the IS96A encoder. Okay, so the speech quality for IS95 was poor. So next we had CDMA Development Group 13 vocoder, also known as the Qualcomm vocoder, code excited linear prediction. It is actually a variable rate speech coder that dynamically selects one of 3 to 4 available data rates for every 20 millisecond speech frame depending on voice activity and energy in the speech signal. So previously all speech signals were transmitted at a particular data rate, but then it was Qualcomm designed a variable rate data encoder which according to the energy level or the voice activity of the particular 20 millisecond duration will choose a particular rate from the 4 available rates. So the pitch and codebook parameters determined in an analysis by synthesis approach using an exhaustive search over all possible parameter values. So it searches all the possible parameter values and it is done. So this is the enhanced the variable rate coder. Next, error correction coding. One speech coding is done, another kind of coding is done is error correction coding. So error correction coding is 8.6 kbps in the and 13.3 in uplink and 8.6 and 13.3 kbps error rate coding in downlink. Okay, so now we come to error correction coding for 8.6 kbps in the uplink. So forward error correction is different for 8.6 and 13.3. However, it is identical for two existing vocoders that are based on 8.6 kbps output. So these vocoders are associated with rate set 1 and thus have the following encoding steps. So encoding starts with 172 bits for each 20 millisecond frame from the vocoder. Okay. Next, in the next step, 12 frame quality indicator bits are added. These bits act as parity check bits and allow determination of whether the frame has arrived correctly or not. So these are basically there as redundancy for parity check. Then adding an 8-bit encoder tail to flag whether to flag that basically what you have sent is an encoder. So to flag that you add an 8-bit encoder tail, and that will bring the total number of bits to 192. These bits are then encoded with a rate 1 by 3 convolutional encoder with constant length 9 Okay, the three generator polynomials. So basically now you pass them through a 1 by 3 convolutional encoder with the following three generator polynomials. Next, for the CDG13 encoder, so for 13.3 kbps in the uplink, encoding steps are in principle similar but different numerical values. So encoding starts with 267 bits, a frame erasure bit is added, and a total of 12 frame quality indicator, basically redundancy bits, and 8-bit tail to 8-bit tail to flag the presence of an error correction bit. So if that 8-bit pattern is there, then the system will interpret that it is a error correction bit. Now, okay. Similarly, error correction coding for 8.6 kbps outlier, same for in the downlink again. It uses the same principle, but it uses a RAID 1 by 2 convolutional encoder, and the generator polynomials are such: 1 plus d plus d square plus d cube plus d5 plus d7 plus d8 and another. Okay, so now next interleaving is done. So output from the convolutional encoder is sent through a block interleaver, and this interleaver creates a interleaving pattern, and that is shown to reduce the bit error rate probability. Next is the spreading and modulation parts. So long and short spreading codes and Walsh codes. So IS95 uses three types of spreading codes: Walsh code, short spreading code, and long code. So Walsh codes are strictly orthogonal codes that can be constructed systematically. Okay, so Walsh code, we know that the Walsh-Hadamard matrix you generate from the Walsh-Hadamard matrix, you take a row and you get the Walsh code. So the Walsh code in IS95 are the columns of the component of H hat 6. So H hat 1, you start with 1 1 minus 1 1 1 1 minus 1, and then you construct H hat n plus 1 as this, and H hat like that you go from H hat 2 3 4 5 6. When you reach at H hat 6, you would have got the uh, Walsh code for IS95. So each column of H hat 6 is the Walsh code. Next, there is two spreading codes which are generated using PN sequences. So they use a shift register of length 15. So they use generator polynomial sequences. And another is long spreading code that uses a shift register order of. Okay, so now there is also long spreading code. The long spreading code uses length of 42. Okay, so the logical and physical channels that are present in IS95 are IS95 are um, this traffic channels. The traffic channels carry the voice data. So they have rate set 1 and rate set 2. So they have the different rates. And the next, these source data, that is output from vocoder, are possibly repeated and then convolutionally encoded and interleaved. The data are subsequently spread and modulated. The spreading and modulation operations are different in the uplink and downlink. A number of control messages are also transmitted on traffic channel. So for the uplink, power measurement report, pilot strength measurement, handoff completion, etc. So number of control messages are also transmitted in the traffic channel. Next is the access channel. The access channel is a channel in the uplink that is used for signaling users without a current call. So access channels basically manage the users which are not currently participating in data communication to keep them in the network. There is access channel. It includes security messages, page response, registration, etc. The access channel uses a source data rate of 4.8 kbps. Spreading and modulation is very similar to uplink traffic channels with same data rate. However, no gating is done and all repeated symbols are actually transmitted. Since the access channel is spread with a long spreading code, a considerable number of access channels can exist. As a matter of fact, up to 32 access channel exist for each paging channel. Okay, and next is the pilot channel. The pilot channel allows the MS to acquire the timing for a specific base. So MS, the user acquires the timing for a specific base station after the transfer connection from base station to mobile station and estimate the signal strength for all base stations in the region of interest. Okay, so the pilot channel will be similar to the downlink traffic channel, but it will have some important peculiarities which will distinguish it from traffic channels. It is not power controlled. So it uses Walsh code 0 for transmission. So it has a higher transmit power, so it has no spreading. It has higher transmit power than traffic channels. Because of its importance, typically 20% of the total BS power is assigned to pilot channel, and the pilot channel is easy to demodulate because it is an all zero sequence spread by short spreading code. The only difference between pilot transmitted from different BS is temporal offset. After an MS is acquired and pilot, it can more easily demodulate the synchronization channel, as the timing of that synchronization channel is locked to the pilot. So basically the pilot is same and it is known, and even the delay of it is very easy to interpret for a say, mobile station. Now next is the synchronization channel. The synchronization channel transmits information about system details that are required for the mobile station to synchronize itself to the network. So that is basically the network identifier, the offset, the system time, the local time. These are all needed to synchronize for the user to synchronize with the data. Okay. Okay. So synchronization channel is this, and apart from that, yeah. So mapping logically in the downlink, mapping is done in rather so logical channels to physical channels. How it is done? So logical channel is decided by the base station, and physical channel is what is actually present, the frequency resources that are actually present. In the downlink, mapping is done in a rather straightforward way. Different channels are assigned different Walsh codes for spreading. Specifically, the pilot channel uses Walsh code 0. The paging channels use Walsh code 1 through 7. The synchronization channel uses Walsh code 32, and the traffic channels use all other Walsh codes. So in the uplink, only traffic channel and access channels exist. These are assigned different long spreading code and thus mapped to different coding channel in all cases. So that will be all for